If for a square matrix A, given that A into adjoint of a 3 by 3 matrix, 2025, 0 and 0 and 0 2025 and 0 and 0 0 2025. On the right side, we can just consider 2025 common, and we can write 1 0 0 0 1 0 0 0 1, which is an identity matrix of order 3. So we can write 2025 into identity matrix with order 3. So we can consider the matrix A with order 3, and here A into adjoint of A, the left side. And we had a property A into adjoint of A is equal to determinant of A into identity matrix of order, which is a order of matrix A, that is In, where n is the order of matrix A. So when comparing here, 2025 can be taken as determinant of A and identity matrix of order 3. So determinant of A is equal to 2025. And also we know that determinant of adjoint of A is equal to det A to the power of n minus 1. Here n is equal to 3. So we can write det A 3 minus, that is 2. So determinant of adjoint of A is equal to det A whole square. Determinant of A is 2025 whole square. So finally we can say that determinant of A plus determinant of adjoint of A is equal to 2025 plus 2025 whole square. So which is our option D. So option D is the answer. Assume X, capital Y, capital Z, W and P are matrices of orders given. So X is a matrix with order 2 by n, and Y is a matrix with order 3 by k, and Z is a matrix with order 2 by p, and W is a matrix with order n by 3, and P is a matrix with order small p by k. And it's given restriction on n, k and p so that py plus wi will be defined. So we know that a matrix, if A is a matrix of order m by n and B is a matrix with order n by p, then the multiplication of these two matrices AB is defined only when the number of columns in the first matrix should be equal to number of rows in the second matrix, and the order of the matrix AB can be taken as m by p. So these are the conditions to define for AB to be defined for multiplication. So let us see here Py. So P is a matrix with order p by k, and Y is a matrix with order 3 by k. Now the Py is a matrix to be defined only when this k should be equal to 3. The number of columns in first matrix should be equal to number of rows in the second matrix. So k must be equal to 3, and the order of this matrix can be taken as Py matrix order can be taken p by k. Similarly, W is a matrix with n by 3, and Y is a matrix with 3 by k, and here we can see that the number of columns in first matrix is equal to number of rows in second matrix, so the multiplication is possible, and then the order of this Wi matrix is, we can say, n by k, that is n by k. And now for adding, Py is a matrix and Wi is a matrix. Addition of two matrices is possible only when their orders are same. So Py matrix order is p by k, and Wi matrix order is n by k. So for addition, since the order must be same, so we must consider p should be equal to n here. Anyhow k is same, so p must be equal to n. So to define py plus wi with the respective orders, so we can consider p must be equal to n and k is equal to 3. So we can go with an option A. We need to find the interval in which the function defined by f of x is equal to e to the power of x is strictly increasing. Let's differentiate the function with respect to 2x. So we have f dash of x is equal to e to the power of x, and we know that e power x is always greater than 0 for every x belongs to R. Since if we can see the graph, we know the value of e is approximately equal to 2.7. So when x is equal to 0, e power 0 is 1. So we can consider the point here. And when x is equal to 1, e power 1 is 2.7. 2.7. So we can mark here. So here is the point. And when x is equal to 2, e square value approximately equal to 7.3, let us say. So we can mark e square 7.3 somewhere here. And if we can consider the negative number minus 1, e to the power of minus 1, that is 1 upon e is 0.3 approximately. So we can say 0.3. So here is the point, and it keeps on decreasing, but it cannot be equal to 0. E power x cannot be equal to 0 for any x. And hence we can see the graph. It is always positive, and e power x is always greater than 0 and even cannot be equal to 0, and hence we can say this function is strictly greater than 0, or we can say even the differentiation is positive, this is f is strictly increasing, and this function is increasing on entire real numbers on x belongs to R, that is minus infinity to plus infinity. So we can go with an option C. Given that A and B matrices are non-singular matrices, that is determinant A is not equals to 0 and determinant of B is not equals to 0 with the same order, and with the determinant of A is 5, and we need to find the determinant of B inverse into A into B whole square. We had the property determinant of AB is equal to determinant of A into determinant of B. Our determinant of ABC is equal to, if ABC are matrices with the same order, we can say determinant of A, determinant of B into determinant of C. So here we can write determinant of B inverse into determinant of A and determinant of B whole square. And also we know the determinant of A inverse is equal to 1 upon determinant of A. So determinant of B inverse we can write 1 upon determinant of B into determinant of A into determinant of B. Since determinant is a constant, we can cancel them. So determinant of B and determinant of B is not equals to 0, we can cancel them, and we can say determinant of A whole square, and determinant of A is given 5, so we can write 5 square, which is 25. So 5 square is the answer, which is option B. We need to find the value of n so that the differential equation x to the power of n into dy by dx, which is equal to y times of log y minus log x plus 1 is homogeneous, where x and y are positive real numbers. And we know that the function dy by dx or the equation dy by dx is equal to f of x comma y is said to be homogeneous differential equation if for lambda some real number constant f of lambda x comma lambda y is equal to lambda to the power of n into f of x comma y. It's a homogeneous differential equation of order n. So let us write it in the form of a dy by dx is equal to f of x comma y. So we can write dy by dx is equal to y divided by x power n, and by using the properties of logarithms we can write log a minus log b is log a by b. So log y upon x, and 1 we can write it as log e to the base e, because the base is logarithm. Logarithm in base is e. So y divided by x to the power of n, again by using the properties of logarithms, log a plus log b is log ab. So we can write y into e divided by x. So this is dy by dx is equal to, which is in the form of f of x comma y. Now consider f of lambda x comma lambda y, which is equal to lambda y divided by lambda x whole power n into logarithm of lambda y into e divided by lambda x. So here we can cancel the lambda. It's a non-zero real number. So we can write lambda divided by lambda power n into y divided by x power n into log of y e divided by x, which is considered as f of x comma y. So lambda to the power of 1 minus n f of x comma y. We got f of lambda x comma lambda y is equal to lambda to the power of 1 minus n of f of x comma y. And for n is equal to 1, it becomes 0, degree 0. This is a homogeneous function of degree 0, homogeneous differential equation of degree 0 if we consider n is equal to 1. So n is equal to 0 and we cannot consider it because it will not become homogeneous. So we may consider n is equal to 1. So we can go with an option B. That is lambda to the power of 0 of f of x comma y. Given the points say A x1 comma y1, B x2 comma y2, and C x1 plus x2 comma y1 plus y2 are collinear, then we need to find the value of x1 into y2. And we know that if the 3 points x1 comma y1, x2 comma y2 and x3 comma y3 are collinear, then the area of the triangle formed by these 3 points will be equal to 0. Area of triangle formed by these 3 points ABC equals to 0, or we can use the condition. In this case we can use the condition determinant of x1 minus x2, y1 minus y2 and x1 minus x3, y1 minus y3, the determinant is equals to 0. So let's use the same condition here since they are collinear. So we can write mod of determinant of x1 minus x2, y1 minus y2. In the second row, x1 minus of x3, x3 is nothing but your x1 plus x2, and here y1 minus of y1 plus y2, which is equal to 0. That is x1 minus x2, y1 minus y2, and after simplification we will get here minus x2, and here we will get minus y2 is equal to 0. So let's expand the determinant. So we get minus y2 times of x1 minus x2 plus x2 times of y1 minus y2 is equal to 0. or we can write minus y2 x1 plus x2 y2 plus x2 y1 minus x2 y2 is equal to 0. So x2 y2 gets cancelled. So we can write here x2 y1 is equal to x1 y2, or we can write x1 y2 is equal to x2 y1, which is option A. Option A is the answer. Given matrix A is equal to 0, 1, C, minus 1, A and minus B, 2, 3 and 0 is a skew symmetric matrix. It's a 3 by 3 matrix. Then the value of A plus B plus C is, we know that for skew symmetric matrix, A transpose is equal to negative A, or we can write Aij is equal to negative of Aji, where I is not equals to j, and we can write 0 whenever I is equal to j. So we can give an example: 0, a, b, minus a, 0, and here we can write c, minus b, 0, sorry, negative c and 0. This is the standard form of an skew symmetric matrix. So when you can see here a must be equal to 0. If A is a skew symmetric matrix, if A is skew symmetric, so A must be equal to, the small a must be equal to 0. And also we can check the C value should be equal to negative of this value, that is C is equal to negative 2, and B value, and here negative B is there. So 3, and it should be negative 3. So B must be equal to 3. So therefore A plus B plus C is equal to 0 plus of 3 plus C value is minus 2. So that is 3 minus 2 is 1. To make this matrix A skew symmetric, the value of A plus B plus C must be taken as 1. So option A is the answer. For any two events A and B, it's given that P of A bar means, which is P of probability of not getting an event A is 1 by 2, and probability of not getting an event B is 2 by 3. So which implies that probability of getting an event A is 1 minus P of A bar, that is 1 minus 1 by 2, which is half. Similarly, probability of getting an event B is equal to 1 minus P of B bar, which is 1 minus 2 by 3, which is 1 by 3. And also given P of A intersection B is equal to 1 by 4. So we can find P of A union B, which is equal to P of A plus P of B minus P of A intersection B. So P of A is 1 by 2, and P of B is 1 by 3, and P of A intersection B is 1 upon 4, and here the LCM is 12. So 2 here 6 times, and 3 4 times, and 4 3 times. So 10 minus 6 plus 4, 10 minus 3, 7 7 upon 12. So P of A union B is equal to 7 upon 12, which implies that P of A union B whole complement is equal to 1 minus 7 upon 12, which is 12 minus 7, that is 5 by 12. And by De Morgan's law, we can also write A complement intersection B complement is equal to P of A union B whole complement, which is equal to 5 by 12. Now by using the formula P of A bar by B bar, which is equal to P of A bar intersection B bar divided by P of B bar, which is 5 by 12 divided by P of B bar is 2 by 3, or we can write 5 by 12 into 3 upon 2. So 3 4 times, and here we can write, so 5 divided by 8. So 5 upon 8 is the answer for this question. Option C is the answer. We need to find the value of alpha if the angle between the two vectors P and Q is obtuse angle. We know that if theta is the angle, or let us consider theta be the angle between two vectors, vector P and vector Q, so which is obtuse. So we know that if theta is the angle between the two vectors, if theta is acute, cos theta is positive, and cos theta is negative when it is obtuse angle. So for obtuse angle, we need to consider cos theta is negative. So which implies cos theta is less than 0. That is P dot Q dot product should be negative. So we can write 2 alpha square I 2 alpha square I minus 3 alpha j plus k dot product with I plus j plus alpha k should be less than 0. That is 2 alpha square into 1 minus 3 alpha into 1 plus 1 into alpha should be less than 0. That is 2 alpha square minus 3 alpha plus alpha is less than 0, or 2 alpha square minus 2 alpha is less than 0, which implies that 2 alpha taken common, alpha minus 1 is less than 0. By using the wavy curve method, alpha 0 and alpha is equal to 1. So negative for 0 to 1. So alpha must belongs to 0 to 1. So we can go with an option B. Given that modulus of vector A is equal to 3 and modulus of vector B is equal to 4 and modulus of vector A plus B is equal to 5, we need to find modulus of vector A minus B. So let us consider mod of A minus B is equal to x. So on squaring on both sides, so we can write mod of A minus B whole square is equal to x square. Since we know that the property mod A square is equal to A dot A, so we can write A minus B dot A minus B is equal to x square. That is A dot A minus B dot A minus A dot B plus B dot B is equal to x square. That is mod A square minus A dot B and B dot B both are same. A dot B is equal to dot product is commutative. So A dot B is equal to B dot A. So minus B dot A minus A dot B, we can have 2 times of A dot B plus B dot B, that is mod B square is equal to x square. And mod A square value is 3 square minus 2 times of A dot B plus mod B square is 4 square is equal to x square. That is x square is equal to 9 plus 16, that is 25 minus 2 times of A dot B. Keep it aside. And now let's consider mod of A plus B is equal to 5. And now squaring on both sides, mod A plus B whole square is equal to 5 square. So by using the same concept, we can write mod A square plus mod B square plus 2 times of A dot B is equal to 5 square is 25. So mod A square is 3 square and mod B square is 4 square plus 2 times of A dot B is equal to 25. So here 9 plus 16, 25. 25 plus 2 times of A dot B is equal to 25. So which implies that A dot B must be equal to 0. So substitute A dot B is equal to 0 in the equation 1. From 1 we can write x square is equal to 25 minus 2 times of 0. That is x square is equal to 25. So which implies x is equal to 5. X is nothing but mod of a minus b. So therefore mod of a minus b vector is equal to 5. So option C is the answer.